All right, so welcome back to Network Attack and Defense Segment 1, and this is Part 2. So, network traffic in a LAN is usually handled by switches inside a LAN. A switch is officially, technically, it's a network bridge that uses MAC addresses to process and forward data. So switches, physical switches look like this. They have a bunch of ports. Small ones that you might buy for in-home use might only have 4 or maybe 8 ports, whereas ones that are used in large organizations might have 48 or maybe even more ports that you can connect various LAN stations to. Almost always switches are OSI layer 2 devices. So OSI is Open Systems Interconnect, and it's like a network default way of layering networks. There are switches that might perform layer 3 functions like routing. Routing is definitely in OSI layer 3, and switches are supposed to usually layer 2. We'll just consider them to be layer 2 and as far as this discussion is concerned, but you might want to know that there are multi-layer switches. Virtual switches are coming into use a whole lot these days with the use of virtual machines. So if you use virtualization software like VirtualBox, Xen, VMware, or Hyper-V, they all come with virtual switches. So this is roughly what they would look like. You have a virtual switch to which you connect various virtual machines that you're running on your system, and they have basically what looks like or what is treated like a network card or a network interface card, a NIC, but it's actually just software running in memory, and you're not connecting these things via cables. So I'm going to scroll back up to the previous slide. So physical computers are connected using cables, Ethernet cables in this case, or fiber optic cables or something like that. But in virtual machines and virtual switches, they're just connected by memory. It's like a function call that emulates network interface cards and switches. So both NICs and switches in a virtual environment, they are just programs running in memory, and they can be connected to the physical Ethernet adapters of actual machines, and that can take them to an outside or external local area network and even the internet. So that's how your virtual machines can get connected to the internet, is through virtual switches and then physical adapters, and from there to external switches and routers all the way out to the internet. So there are virtual multi-layer switches like Open vSwitch, which implements switching completely in software, and virtual security switch also implements isolation of virtual machines, and you can even do like packet filtering and content inspection of network traffic going between virtual machines. So we talked about switches being officially bridges, and bridge devices were things that were used in the past. They are not used so much. Physical bridges are no longer used because there are some problems as far as traffic, managing traffic, and these days switches are probably what you would see in most organizations. So a bridge is something that moves packets between two or more network segments. It is a layer 2 device like a switch. It uses MAC addresses as well. And these days, the place where you would see bridges is with things like Docker containers, which are becoming very popular in delivering apps, web apps, things like that. So now we move on to routing or layer 3 activities. So routers are definitely things that examine the IP addresses, and IP addresses are layer 3 addresses. So what a router does is it moves packets between two or more network segments. So these are, let's say, LANs. This would be one segment. This is actually a LAN by itself connected to a switch, and here's another switch also connected to this router, or there might be a switch in between. So you might have this router connected to one switch, which is then connected to three other switches, which are each connected to many different LAN stations or computers. So what a router does, it moves packets between two or more of these networks. So in this case, it looks like this router is connected to two other routers and three switches, and so it would have to have 5 interfaces altogether. And so what it's doing is moving packets that are coming from any of these 3 networks or local area networks that's coming from one connection coming from each of these switches to either one of these 2 routers. And although not shown here, it's very likely that there's going to be a router in one of these networks that is connected to the internet. So these routers typically implement a dynamic distributed shortest path algorithm to find the best routes to whatever destination a packet is going to. Okay, so remember, routers are layer 3, and what in OSI, the layer 3 is the network layer, or the internet protocol is one of those protocols that sort of live at this layer. So things to keep in mind about the internet protocol IP: it's a stateless protocol in the sense that it doesn't keep track of past history, and it just transfers. All it has to do is it has to transfer a packet from one machine to another. So typically, all the examples that we will look at are going to be IPv4. Remember, it uses 32-bit IP addresses written as 4 decimal numbers with separated by dots. And so each one of those numbers, because it's 8 bits, go from 0 to 255, giving us a total of 32-bit IP addresses. And 2 to the 32 is a little bit more than 4 billion. So IPv4 only has a maximum of 4 billion unique addresses. As of 2012, there are about 9 billion devices on the internet. It's going to be a lot more now. And so you might ask, do they all use IPv4? No, they don't all use IPv4, but a majority of them do. And even then you might ask, well, how can they have different unique addresses? They can't. So it turns out what we usually do is use private IP addresses like 192.168.1. something. Those are, if you see the 192.168, that's definitely a private IP address. So that's not going to be unique. That's only going to be unique within the LAN. Outside the LAN, if you see in the internet an address like 192.168, there must be some mistake, because no router is supposed to send out a packet with that destination, an address like that, 192.168. There's a bunch of those, and we're not going to go over them here, but there are a bunch of private IP addresses that you can use, and that's really how most networks handle this limit of 4 billion unique addresses. A lot of machines are going to have the same addresses, but they can't be seen by each other because they're behind some router that won't forward those messages. Another way to get over this addressing limit and also to improve security is to use the new standard, which is IPv6. This uses 128-bit IP addresses. And so if you calculate 2 to the 128, that is a huge number. And so it's very unlikely that we will exhaust the number of IPv6 addresses. However, there are a few problems with IPv6. There is a lot of advantages to using it. It is usually written as hexadecimal numbers, and it's not very intuitive for a lot of people. If you're a computer science major or something like that, you're probably used to hexadecimal numbers, but the general public, they are not, and so it's a little bit let's say, clunky to use for regular people. For now, most systems that you buy these days, if you buy a laptop or a desktop or a smartphone, the chances are they will use both IPv4 and IPv6. The plan was to switch to IPv6 only, but for whatever reason, it sure doesn't seem to be happening. It seems like for the near future at least, we are going to have machines with both IPv4 and IPv6, and the use of IPv4 seems like it's only expanding, even though we've exhausted the unique addresses. Look, one of the reasons why we can do this is because actually not every machine needs to have a unique address, so there are ways around it. Okay, so that was layer 3, and next up is layer 4. One of the two protocols that are commonly used in layer 4 is TCP, Transmission Control Protocol. TCP is a OSI layer 4 protocols, and it's responsible for ordering and making sure that traffic that's meant for a destination actually reaches its destination. So I'm going to scroll back up, and remember that the layer 3 protocol, IP, is a stateless protocol. That is, it doesn't keep track of past history, and so it will do its best to get a packet to its destination, but it cannot guarantee that. What has to guarantee that is a set of a protocol above it, and the one that we will be looking at right now, I guess, is TCP. And so TCP is responsible for making sure that if you try to send something out, it gets there. So TCP runs on top of IP. It uses IP, and it provides what are called virtual circuits for sending packets. That is, you have some kind of route going from point A to point B through which a set of packets will go, and then if you have to, for example, send a large image, you're not going to be able to send like a megabyte sized image as a single chunk of network data. Instead, what you would do is you would take that megabyte image that you have to send, split it into a bunch of IP packets, and then send each one, and then you would also probably only send maybe some of them at a time to make sure that once they all get through, then you can start sending the next batch of packets, and so on. So there are all these schemes that are used in TCP to control this flow of packets, and then once it reaches the destination, those packets are put together to create the image that you're trying to send out. If a particular packet fails to reach the destination, then it's this layer that actually keeps track of what was received and what needs to be resent because maybe something happened to it and it wasn't received or wasn't received properly. And so the TCP layer is responsible for retransmitting packets if you need packets to be retransmitted. So another thing that you should probably review or maybe take a look at are the OSI layers. So there are 7 layers in the OSI scheme. There are 3 media layers, starting with the physical layer at the bottom. This is responsible for transmitting, taking care of how to transmit these signals at the bit level. That is, are using light and fiber optic, are using the air for Wi-Fi transmission, or cables for Ethernet, things like that. On top of that is data link, which looks at frame level transmission. So things like Ethernet are over here, and so this at the unit of data that you'll be sending out at this layer 2 would be a frame, and layer 3 it'll be, usually we call it packets. Layer 4, and so these other layers, no one sticks to one way of talking about things, but I will try to stick to the term packets for layer 3, and then segments for layer 4. People will use datagram for layer 2 as well, because there are 2 protocols. We talked about TCP. There's also the UDP protocol, which refers to I think Universal Datagram Protocol, and so we might say datagrams for UDP. Some people do that. Some people use datagrams for network, but I will try to stick to packets for layer 3. So notice IPv4 is at this layer, TCP is at this layer, and TCP IP, that's the combination of actually a whole bunch of protocols. It includes layer 4 and layer 3. That's the most common way of implementing these OSI layers, is TCP IP. So when you look at OSI layers, there's many ways to implement the actual networks that use the OSI layer. So this is actually just an abstract way of thinking about networking and communication using networks. For example, you might this is not doesn't happen very often, but you might encounter a U.S. Department of Defense network protocol stack that is different from what is used in most of the internet, in that it might have layers like this. Actually, these are pretty much the same kinds of layers you would find in a TCP/IP stack, protocol stack. That is a stack of protocols, but it might not be completely compatible with TCP/IP. So if you do have a different network protocol stack, you can't just transmit this data and expect the receiving side to be able to do anything with that data, because they have to have the same network protocol stack too. And so you have this standards problem, and as a result, most networks are set up to use TCP/IP, and that's what you would see most commonly on the internet. Well, actually, on the internet, pretty much has to be TCP/IP for the most part. Okay, so TCP/IP looks like this. You have your transport layer protocol. You can use TCP or UDP. Below that is the IP or network layer, and then below that is usually, if you're using wired communication, you might very likely to use Ethernet. You could use Wi-Fi too, and then at the lowest layer is physical transmission media. So if you take a message, as we said, if you have a large image or something, layer 4 or the TCP protocol will chop it up into pieces, segments, and each one of those segments will go down to the next layer, and so this layer 3 or network layer will prepend an IP header to this data coming in from the transport layer, and send that down to the next layer down, which is the data link layer. And if you're using Ethernet, for example, or even Wi-Fi frames, you will put on an Ethernet header. In the case of Ethernet in layer 2, it also has a trailer, and this is usually a frame check sequence. Wi-Fi, you do the same kind of thing. You have a header, and I believe you have a trailer with a frame check sequence for Wi-Fi 2. So this is how messages are sent, and then at the receiving end you get this frame. You take out once you know that this is where the message is headed to, you take out the header and the trailer, and you pass that up to the layer up, which is the network layer, and that layer takes out the IP header, sends that up to the next layer, and then on the receiving side you get a whole bunch of these segments, and you assemble that into, let's say, an image that you send up to, let's say, application which might be a web browser. Right.